Welcome to Agdventures, a journey into the world of proof assistance and formal reasoning. In this first episode, we are starting with a classic, the MIU puzzle from Douglas Hofstadter's Godel Escher Bach. In Chapter 1, Hofstadter introduces the MIU puzzle, a playful system of strings and rules that raises deep questions about logic, formal systems, and what it means to prove something. In this video, we will explore the MIU puzzle through the lens of Agda, a dependently typed programming language and proof assistant. Along the way, I will also contrast it with Rocq just enough to give you a feel for how different proof assistants let us express and verify ideas. The goal isn't just to solve the puzzle, but to show what it feels like to formalize reasoning inside these tools. How rules become types, how derivations become programs, and how proof assistants help us explore the structure of formal systems. So let us begin our adventure, starting with Hofstadter's MIU puzzle and see how Agda and Rocq help us reason about it. MIU system consists of strings composed of three symbols, M, I, and U. There is one given string Mi. There are four rules. Rule 1 says that if a string ends with an I, we can append U to it. Rule 2 allows us to duplicate anything that follows an M. Rule 3 says that if we find three I's in a succession, we can replace them with a U. And finally, Rule 4 allows us to remove a pair of U's. And the question is, does MIU belong to this system? Can I start with Mi and follow the rules and reach MU? Let's go about solving the puzzle in Agda. If this is the first time you are hearing about the MIU system, now is the time to pause the video and try to solve the puzzle. Here is our data type symbol representing the allowed symbols of the system. An MIU string is an alias for list of symbols. The MIU system is encoded in this inductive data type with 5 constructors, one constructor for the axiom, and one constructor for each of the 4 rules of the MIU system. There are some Agda specific nuances in the definition of this type, but I will not dwell much on those here, as we will soon see a very similar but much simpler data type. Our solution to the MIU puzzle relies on the number of i's in a MIU string. Let us go about defining a function for counting the number of i's in a MIU string. Agda allows us to define the function interactively. So I start with a question mark and load the file. Agda replaces the question mark with a hole. We can do several things in the context of such a hole, and we'll see some of those over the course of this video. Right now I'll type Ctrl+C here to ask Agda to perform pattern matching on str. Agda responds with 2 cases, an empty list and a non-empty list case. In the case of empty list, the solution is obvious. So I can type Ctrl+C, Ctrl+A. Agda replaces the hole with 0, which is the number of i's in an empty list. Now, again, I will perform pattern matching on the first member of the list. When the first letter is M, the solution is just calling count I or recursively calling count I on the rest of the string. Same with the case where first letter is U. Only in the case of I where we'll have to increment the result of the recursive call. There, we interactively implemented our first function in Agda. Now let us implement our first theorem. What this theorem says is that for all strings S1 and S2, the number of i's in their concatenation is the sum of number of i's in each. Let me again implement this interactively. I'll put a question mark, load the file. So I will perform pattern matching on S1 again. So we have again two cases where S1 is empty, or S1 is non-empty. In the empty case, you can see right hand side on the right side on the proof window. What we need to prove is that count I of S2 is equivalent to count I of S2, which is Agda will be able to do it automatically. I just have to type Ctrl C Ctrl A. Again, I go to the other second hole. I'll again perform pattern matching on the first character X. So in the case where the first character is M, we can see the goal here is count I of S1 plus S2 is equal to count I of S1 plus count I of S2, which is actually the recursive call here. So Ctrl C Ctrl A will solve it for us. The same is the case with the U case, with the case where the first character is U. The case where the first character is I, the situation is slightly different. Yay. So we proved our first theorem. But let us spend a minute here and see what we did. Alright, before we look at the proof itself, I want to pause on this symbol right here, the equality. In Agda, equality is not a Boolean test. It is not something that evaluates to true or false. Instead, x equals to y is a type. It's a type with two parameters. Somewhat similar to what we saw with the list earlier. We earlier saw that list has a parameter symbol. So given the type symbol, we got the type list of symbols, which we are calling as MIU string. Similarly, equality is a type that takes two values as parameters. That a type can depend on values is what makes it a dependently typed programming language. Moreover, this type is defined such that it can be instantiated only if both the values are equal. If x and y are really the same value, then this type has exactly one inhabitant called refl. If they're not the same, the type has no inhabitant at all, meaning you simply cannot produce a value of that type. Agda won't let you. So when we see something like this whole thing is a type. The type is the statement of the theorem, and its body is the proof of the theorem. This is the Curry-Howard correspondence in action. Types are propositions and values are proofs. Writing a function of this type means, please give me a value that inhabits this type. In other words, please give me a proof that the equality holds. Each pattern matching clause becomes one step in of the proof. The base case gives us refl. Let us do it again. In the base case, the equality is obvious, so the solution is refl. The proof is refl. And in the recursive cases, we peel off the first symbol and rely on the induction hypothesis, which is just the recursive call. When the symbol is I, we wrap the proof with consuct to reflect the extra successor. And Agda checks all of this for us. If any branch does not actually prove the equality it claims, the type checker will complain. So the little function is doing two jobs at once. It's a piece of code and it's a fully verified mathematical proof. I'm not sure if all that made a ton of sense. Let us try something different. Let us come up with a way to assert that a given number is not a multiple of 3. Why would we do that? Because we will see that we can use such an assertion to solve the MIU puzzle. What we want is an ability to say something like not multiple of 3 of x for a given natural number x. And such an assertion would tell us that x is not a multiple of 3. To get such a type, we need we need to understand that non-multiples of 3 come in two flavors. Those that leave a remainder of 1 when divided by 3 and those that leave a remainder of 2 when divided by 3. Let us go about defining such a type. So we have such a type here. It is parameterized over natural numbers and it accepts two constructors, rem1 and rem2. Rem1 is the constructor we need to use for those numbers that leave a remainder of 1 when divided by 3. Rem2 for those that leave a remainder of 2 when divided by 3. Looking at the signature of rem1, we see that it is accepting two arguments, a natural number k and an assertion and a type and a second argument whose type asserts that when k is divided by 3 we get a remainder of 1. How is it doing that? It is doing so by asserting that there exists a number m such that k is equal to 1 plus 3 times m. Similarly, the second constructor takes two arguments, a natural number and a proof that the number when divided by 3 gives a remainder of 2. Now, the only way we can call a number k as not multiple 3 of k is by using one of these constructors, and each constructor requires a proof that the number is indeed a non-multiple of 3. So let us try to instantiate 1 as a non-multiple of 3. So again, let us do it interactively. So in order for us to assert that 1 is not multiple of 3, we will use the constructor rem1. Let us see if Agda, right? Now let us see if Agda can figure it all out. So I'll type Control-C, Control-A, 0, yes. So the m that we care about for proving that 1 is not a multiple of 3 is the 0, m is equal to 0, and we can prove it. Similarly, we can assert that 2 is not multiple of 3. Right. Thank you, Copilot. Right. Oh, I made a mistake somewhere. Multiple, yeah. Right. So we do Control-C, Control-R, then to refine it, and then auto will fill it up for us. Just to be safe, let us see we can indeed prove that, say for example, take a 3 multiple and prove that we cannot make it, or we cannot somehow sneak in a 3 multiple as a non-multiple. So what is it saying? Not multiple. Copilot. Yeah. Right. So let us refine it. Then, so no matter what we type here, for instance, so then Agda is asking us to prove that 12 is equal to 13, right? Which is impossible for us. Or I take 5 here, right? No matter what, I will not be in a position to provide such a proof. So it is impossible for me to construct a not multiple of to assert that 12 is not a multiple of 3. Okay. Now let us prove a congruence that will be useful for us. Oh, nice. Yeah. What we are trying to prove here is that right. So what we are trying to prove here is that given a non-multiple of 3, given a number n which is not a multiple of 3, and another number m such that we have a proof that n is equal to m, then we can assert that m is also a non-multiple of 3. Let me resize this so that we can see the whole signature. Right. Or right. So again, let me do it interactively. Let me do pattern matching on nm3n. Now if you see here, now we know that if here also it would be rem1 only, the same constructor will come in here. Not multiple of 3m, right? Right. And we know if it is the k here, we'll get exactly the k here. Let us also do on k, right? So now we need to prove that m is equal to suc of fst into 3 plus 1 is equal to m, right? But what do we have? We know that n is equal to m, and we know that n is equal to suc of fst into 3, right? So there is a function in the standard library of Agda called trans, which given x equal to y and y equal to z, it will assert that x is also equal to z. We'll use that. So here if we let us see, yeah. So what we now need to prove is that m equal to n, but in the but we have n equal to m, which is n equal to m. So we can rely on symmetry of it. So now we have enough proof there. So Agda will be able to automatically fill it, right? Right. Similarly, this will go the same route. Let me expand x and then I think this is equal to fst, right? Right. So we have proved that given two numbers m and n, and that given that n is not a multiple of 3, and also given that if we have a proof that n equal to m, we can prove that m is also a non-multiple of 3. Relying on Agda's rich standard library, I have proved a bunch of lemmas around non-multiples of 3. I'll uncomment them now. We can revisit them later if time permits. The entire section is to prove these two lemmas. This lemma says that if x is natural number and x is not a multiple of 3, then so is 2 times x. So if x is not a multiple of 3, 2x is also not a multiple of 3. This other guy says that for any natural number x, if x plus 3 is not a multiple of 3, then x is also not a multiple of 3. Now we have all the infrastructure in place. Let us come to our main theorem about the MIU system. What we are saying is that For any string belonging to the MIU system, the number of i's in the string is not a multiple of 3. Let us see if we can prove this theorem. I'll expand on the MIUS. So in order to prove the theorem for the axiom, we need to prove that 1 is not a multiple of 3, which we have already done earlier with a small lemma. So let me reuse that here. Right, so our theorem is proven for the axiom. Let us do it for the rule 1. Let me introduce the variable here, that implicit argument. Right. I'll also increase this guy, right, to make it easier. Now here what we need to prove is that the number of i's in this string is equal to the number of i's in this string. Again, here we can rely on the congruence that we used. So let me type that guy. Right. So now we have two holes here. So what I'm trying to do here is that I'm relying on the congruence and saying that, okay, count I of a string that is ending with I, and the same string when appended with u, the count i's are equal, right? If they are equal, then this theorem is proved. Now, in order for us to do that, we need to prove two things. We have two sub goals. Now, the first goal is to prove that count I of ti is not a multiple of 3, which Agda can automatically infer because we have already proved we have already assumed that the input string is already belonging to MIU system. So it recursively calls the same theorem. So Control C, Control A will prove it for us. Now what we have to do is that we have to prove that count I of a string ending with I is the same as count I of a string of the same string when appended with u. Let us use a lemma for this. Sorry, right. Now if we can prove this lemma and we can rule 1 of t. So if we can prove this lemma, this lemma, then our theorem is true for the rule 1. Now how do we go about this guy? So Agda allows us to do what is called equational reasoning. Looks like Copilot is already doing a bunch of things for us, but we need to prove that right. Let me line these up. So I can provide a step-by-step proof for this lemma. Now, earlier we have proved the distribution of count I over string concatenation, so we can rely on that part here. Count I of s plus count I of which is equivalent to count I of s plus not plus plus count I of So what we are saying is count I of s I is equal to count I of s plus count I of I string containing just I, which is equivalent to count I of s plus count I of IU, which is equivalent to this. But we still need to convince that each of these steps, this is our whole proof, we need to convince Agda that each of these steps are true, right? So here, so in the first step, what we need to prove, count I of s plus I equals to count I of s plus 1, which we have already proved using the count I hyphen right. So the first step is proved. Now here what we are asking, what we need to prove, count I of s plus 1 is equal to count I of s plus 1, which Agda will be able to prove it automatically. So we can eliminate that FL. Right. Now here what we need to prove, count I of s plus 1 is equal to that, which is symmetric of our the count I argument. So count I of right. So with this lemma in place, we have now proved the theorem for rule 1 as well. Now for the rule 2, let me introduce the implicit variable. Like for lemma for rule 1, let me introduce a lemma for this guy as well. Count I of s. Let us prove this lemma, which says that concatenating a string to itself, the count I gets doubled. This should be easy now. Right. This we know, we can prove that this is equal to now we need to prove that count I of s plus count I of s. Okay, let us do it in 2 steps. I'm sure this Agda will be able to figure it out. So this is proven. Now we can rely on this. Okay. There is a plus identity available in Agda standard library. Of counter of s. Oh right, it should be symmetric version of it. I think that should solve the problem. Right. So now we have a lemma which says that appending a string to itself, the counters will get doubled. Now we can rewrite it. T. Right. So now we have already proved a lemma which says that x implies. Let me type it again. Not multiple of 3 of x implies not multiple of 3 of 2x of t counter of So we need to prove that count I of t is not a multiple of 3, which we can prove by recursively invoking the same theorem on the input. Right. So theorem proof 2 is also the theorem is true for rule 2 as well. Now let us prove the theorem for rule 3. Rule 3 is the case where the incoming string has 3 i's in order, and we can then the rule says that we can replace those with u. So let me introduce the implicit variables. Now we have already proved a lemma with if x plus 3 is not a multiple of 3, then we can rely on then we can prove that x is also not a multiple of 3. This is true for the case of so now we will bring in the congruence again. Oh, plus 3. Right. Now let us introduce a lemma for rule 3. Looks like Copilot figured it out. Now if we apply the lemma here in the second argument on T1 and T2, now this should Agda should automatically fill it for us. Yes. So if we prove this lemma 3, we have proved the theorem for rule 3. Now this we can again which should be equal to count I of s plus 3 plus count I of t, which should be equal to which should be equal to this. Let us God, I don't know how to type by the looks of it. Right. Let us prove, Agda, that each and every step of ours is valid. So, right, let us say Kong. Which should be equal to symmetric version of S and U colon T. Right. Right, this should be, Agda should automatically give it for us. Yes. Now, this is associative property of addition. So we should be able to use this. count I of S, count I of T, count I of T and 3. Okay, we need to use the symmetric version of it, I guess. Right. Now, here again we rely on the commutative property of addition. Right. Oh, this is actually this. Now this should automatically, yes. This is our count I. Right. So now we have proved the theorem for rule 4 as well, rule 3 as well. Now let's go to rule 4. Let us go to rule 4. Rule 4 is the case where we can drop 2 consecutive U's. Let me again introduce the implicit parameters. Again, we'll use the congruence here. So let us introduce a lemma. Lemma rule 4. Is equal to Right. If we have this lemma of rule 4, now if we can fill this guy here. Now this we know, this is count I. This should be straightforward. We can remove the refer. We can remove the refer. This should be symmetric version of. So nice. So we proved our theorem for all strings. So we have now proved that every valid string of MIU system is such that the number of i's in it is not a multiple of 3. Now we are ready to confirm that mu does not belong to it. Mu does not belong to the system because mu has 0 i's in it. Let us prove this final bit. So this is just a matter of convincing Agda that no matter what constructor we use, we end up in an absurd state. That is, we are now trying to prove that if n is equal to 0, n is not multiple of 3. So Control C on NAQ. Yes. So we convinced Agda that 0 is not multiple of 3. Now let us drive the final nail in. Let us prove that the mu puzzle. Let us prove that MU does not belong to the mu puzzle, to the mu system. So what is X saying? Yeah. So now we can reuse this guy. Before U and FL. Now we can use our proof to our MIU theorem. Right. So finally, we have now confirmed, we have now proved that the string MU does not belong to MIU system. Let us revisit what we did. We modeled the MIU system as an inductive data type. We introduced another inductive data type to capture the notion of a number not being a multiple of 3. And we proved that MIU system preserves this notion of a number not being multiple of 3 for the number of i's in its strings. And using that, we confirm that mu is not a part of MIU system. Note the proofs in these lemmas. We did a step-by-step proof starting and convincing Agda at each step that our steps are valid. In the next few minutes, I'll spend some time proving the same thing in Rocq. I'll not prove all the theorems, but just a few to give you an inkling of how we prove things in Rocq with all its tactics. So this is our data type. This is the equivalent data type for not multiple of 3. We are calling here not 3 multiple. Let us prove this little theorem which says that for all natural numbers n, if n is not a multiple of 3, 2n is also not multiple of 3. Copilot is trying something, but this is definitely not correct. It should be 2k, I guess. Right. So we rely on these tactics like inversion, destruct, and LIA. LIA stands for linear integer arithmetic to prove things in Rocq instead of equational reasoning. Let us do another simple example. Here we will prove that 1 is not a multiple of 3. Yeah. In Rocq as well, we used exactly the similar data types. And our MIU system follows this similar pattern. Now, let me do one last proof here. Let me prove one last lemma here. So what we are saying is, if the equivalent of count I hyphen plus plus that we did in Agda, let us prove it in Rocq. I will do induction on S1. So this should be simple. Reflexivity. This reflexivity is another tactic in Agda. Now I will do induction on okay, let me rephrase this so that I have valid names there. Now simple. Now let me do induction on X so that right. Done. So as you can see, using tactics, we get a completely somewhat different experience with Rocq on how to prove lemmas. We can finish it off with this as well. Again, here we can, I think we can rewrite again. Let me introduce a rewrite G. Let me introduce another. Okay, let me call it G2. Count underscore I. Right, done. So we proved all the theorems similar to what we did in Agda, and finally we proved even in Rocq here that mu is not derivable in mu. This theorem is insisting that mu is not a part of MIU system. So okay, one last thing. Let me leave you guys with a homework. In chapter 2 of GEB, Hofstadter introduced a PQ system. Try to prove the following theorem related to it. Feel free to share your gists in the comment section. What we need to prove is that the PQ theorem for all XYZ which are hyphens, prove that PQ system of XYZ and XYZ is a PQ system, then length X plus length Y is equal to length Z. Alright, now I'm done. Thank you so much. Thanks for watching.